Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to your favorite Shridevi classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our class 12th physics in chapter electric circuit we'll discuss two very fundamental and universal circuit analysis law of Kirchhoff, that are Kirchhoff current law KCL and Kirchhoff voltage law KVL, and in next 20 minutes we will discuss these laws and their simple applications. Let's start. In the year 1801, Volta has discovered first chemical cell and introduced our subject of current electricity. In next 4 decades, remarkable work has been done in the field of electricity and magnetism. In the year 1847, a German physicist Robert Gustav Kirchhoff introduced two very important electric circuits law by which the analysis of complex electric circuits involving several elements become possible. Now these two law, one is Kirchhoff current law KCL and other one is Kirchhoff voltage law, are based on two conservation law. Kirchhoff current law is based on law of conservation of charge and Kirchhoff voltage law KVL is based on conservation of energy. So both KCL and KVL are fundamental and universal in application. So KCL and KVL can be used to both AC and DC supply circuits, and KCL and KVL can be used both for steady state conditions or short time transient conditions. Let's study these two law KCL and KVL first, and then we'll see some simple applications of KCL and KVL. Kirchhoff current law is applicable to a node point or a junction. A junction or node is that point in electric circuit where more than two branches meets. And as per Kirchhoff current law, the algebraic sum of all the currents at a junction or node point is 0. Summation of current at a junction is 0. Now when we consider algebraic current, there are two type of current. One incoming to junction and second outgoing to junction. If we treat incoming current positive, then here I1, I2 and I6 are positive current, and the remaining current I3, I4 and I5 are outgoing current taken as a negative, and algebraic summation become 0. If we segregate all positive terms and all negative current terms to two sides, we can also state Kirchhoff current law as sum of all incoming current is equal to sum of all outgoing current. And the second format of Kirchhoff current law reduce stress of assigning sign positive or negative to a current and makes our calculations simple and error free. Though both these format, algebraic sum of current is equal to 0 at a junction or sum of incoming current is equal to sum of all outgoing current, are in practice, but it is advised that you follow this second format where we take all incoming current to one side of equation and all outgoing current to the other side of equation and put a equality sign between two format for KCL writing to reduce stress and possible errors. Kirchhoff current law is also known as point law or a junction law, and according to it, at a junction, sum of all incoming current shown in yellow highlight is equal to sum of all outgoing current shown in blue frame, and equation can be written like this. This Kirchhoff current law is based on conservation of charge, and in a certain time interval, amount of charge incoming to junction by incoming current is equal to amount of charge leaving the junction through outgoing current. Since conservation of charge is a fundamental and universal law, so KCL is also universal and fundamental, and Kirchhoff current law is applicable to both DC circuits as well as AC circuits. The utility or application of Kirchhoff current law can be understood by few examples. As in this circuit, we have given two resistance, one unknown R ohm resistance and second 3 ohm resistance, and they are connected in parallel to a 12 volt voltage source, and voltage source supply 6 ampere current to this circuit, and we have to find out the value of this unknown resistance R. Now the value of this unknown resistance can be obtained if we know its voltage, and in this simple circuit, as 12 voltage applied across this R, so the voltage of this unknown resistance is 12 volt. So using Ohm's law, if we know the current passing through this unknown resistance, we can find out the value of unknown resistance. Now to find out this current of unknown resistance, let's make this current as X, and let's find out current in this other branch 3 ohm resistance, which is also connected across 12 volt source. So as per Ohm's law, its current is 12 by 3 4 ampere, and if we apply Kirchhoff current law at this junction point P, P, then incoming current 6 ampere is equal to outgoing current X and 4, and simplification results as the value of X current in unknown resistance as 2 ampere. And now we can apply Ohm's law. The voltage across unknown resistance is 12 volt and current through unknown resistance is 2 ampere, and ratio of voltage to current is unknown resistance and it is 6 ohm. Now the same example can be extended to more than 2 parallel connected resistance. In this circuit, 3 resistance branch, 6 ohm unknown resistance R and this third resistance are connected parallel to a 12 volt source, and this source supply 10 ampere total current to this circuit, and the third resistance branch draw 5 ampere current, and we have to find out the value of this unknown resistance R. Again, the value of R can be obtained by Ohm's law with value of voltage across R, which is known to us 12 volt, and current through R. Let current in this unknown resistance R is X, and if we determine this X, we can find out value of unknown resistance R. Now voltage across 6 ohm is 12 volt, so the current in 6 ohm resistance is 12 by 6, 2 ampere, and if we apply Kirchhoff current law to this node P, we can say incoming current 10 ampere is equal to sum of all outgoing current, and current in 6 ohm branch is 2 ampere, current in unknown resistance R branch is not known to us, let this is X, and the third current is 5 ampere, and when we simplify, we'll get that current in unknown resistance branch X is 3 ampere, and when we apply Ohm's law, the unknown resistance is voltage divided by current. Voltage of R resistance is 12 volt, current in this unknown resistance is 3 ampere, so unknown resistance is 4 ohm. In this complex network consists of 4 nodes and 9 branches. We have to find out current of this branch leaving junction C here. At first sight, the 2 incoming current P and N are not known to us, so it looks X is very difficult to find out. But if we apply Kirchhoff current law to all junctions, we can find out first the value of P and then the value of N, and finally we can find out value of X. If we apply Kirchhoff current law at junction A, the incoming current 10 is equal to outgoing current 3 and the value of this branch current M can be obtained as 7 ampere, and this 7 ampere is incoming current to junction B and 5 ampere is outgoing current at junction B, so the remaining P current is 2 ampere. Similarly, at junction D, incoming current is 20 and one outgoing current is 7, so the remaining outgoing current is, as sum of incoming current is equal sum of outgoing current N and 7 sum, and some simplification results as value of N equal to 13 ampere. Now N is 13 ampere, P is 2 ampere, both are incoming current, and sum of incoming current 2 and 13 become outgoing current, and X current obtained as 15 ampere. One interesting fact is that Kirchhoff current law can be applied to group of junctions or to an area, and if we apply Kirchhoff current law to this area enclosing all those 4 nodes, so at this area sum of incoming current 10 ampere and 20 ampere is equal to sum of outgoing current 3 ampere, 5 ampere, X and 7, and when we simplify this equation in one step, we can find out unknown current X equal to 15 ampere. Kirchhoff voltage law is applicable to a closed part of electric circuit known as mesh, as shown in this yellow highlight or as shown in this blue frame. According to Kirchhoff voltage law, in a closed part of a circuit or a mesh, the algebraic sum of all voltages, whether that voltage is an EMF source or a IR voltage drop in a resistance, algebraic sum of EMF and IR voltage drop is 0 in any loop. Kirchhoff voltage law is also known as mesh law, and it is based on conservation of energy. Since conservation of energy is a fundamental and universal law, so Kirchhoff voltage law is also a fundamental and universal law that is applicable to both DC supply circuits as well as AC circuits. When we are applying Kirchhoff current law as algebraic sum of current at junction A is equal to 0, we have taken algebraic sign of incoming current as 1 and algebraic sign of outgoing current another, and our law simply become sum of incoming current is equal to sum of outgoing current. Similarly, when we are applying Kirchhoff voltage law in a loop or a mesh, we have to start our travel from one point in a mesh and have to move across all elements and come back to the same point, and on the way, whether the elements are EMF source or resistances, we have to make summation of EMF EMFs and voltage drop in resistance, and algebraic sum of all those voltages is 0. Now when we decide sign of voltages for algebraic summation, we consider rise in voltage and drop in voltage, and for calculation of rise in voltage or drop in voltage, we have to consider two end of an element as high potential and low potential, and according to our travel direction across element, there would be either voltage drop or voltage rise. Let's explain calculation of rise and drop of voltages across first EMF source and then a resistance. In a voltage source, the positive terminal denoted by longer arm is a high potential terminal and the other negative terminal is low potential terminal. And if we move across EMF source from high potential to low potential, a voltage drop will take place, and for reverse movement from low potential to high potential, a rise in voltage takes place, and in both conditions rise and drop of voltage is equal to source EMF value irrespective of amount of current in this EMF source. So we can understood that voltage rise or voltage drop calculation of an EMF source doesn't depend upon current through that EMF source irrespective of current value. A movement from high potential to low potential means voltage drop, and a movement from low potential to high potential means a rise in voltage, and rise and drop of voltage is equal to source EMF magnitude. Whereas in a resistance element, voltage rise or voltage drop calculation all depends upon direction and magnitude of current passing through resistance. In a resistive element, current direction is from high potential to low potential. So as per current direction, the two ends of resistance can be termed as high potential terminal and low potential terminal. And if our travel direction is along the direction of current, that means we are moving from high potential to low potential, a voltage drop will take place across resistance, and in vice versa condition, when our travel movement is against the direction of current, we are moving from low potential to high potential, and a voltage rise will take place. And as per Ohm's law, the amount of voltage across a resistance is given as V is equal to IR, and magnitude of current will decide the magnitude of voltage rise or voltage drop in our travel condition. So when we apply Kirchhoff voltage law in any closed part of circuit or mesh, we have to travel from one point in the loop across all elements and come back to the same point. And during travel, when we cross an EMF source, the algebraic sum of EMF, and when we cross a resistance element, algebraic sum of IR voltage drop in resistance is taken equal to 0. And if we take algebraic sign of voltage rise 1 and algebraic sign of voltage drop another, we can rewrite the same Kirchhoff voltage law as in a closed part of circuit, the summation of voltage rise is equal to summation of voltage drop. Let's understood application of Kirchhoff voltage law with some examples. In this given circuit, we have given two voltage source and two resistances in a closed loop, and across these 2 points A and B, we have to find out potential difference. Now to find out potential difference between 2 points, we have to travel from one point to another point, and on the way we have to calculate voltage rise and drop, and the result of that calculation will give us desired potential difference between A and B. Now to find out that potential difference, we need current of these resistances, and in this single loop, let's assume that this current is I and it is circulated in anti-clockwise direction as shown here, as current will usually come out from bigger magnitude of EMF source from positive end. Now to find out this unknown current, we have to use Kirchhoff voltage law equation, and to write KVL equation, we will start our journey from A position and cross this source, come to junction B, cross 2 ohm resistance, come to junction B, then we cross 3 ohm resistance and 2 volt source and come back to the same point. And in our travel of AM, B and A, as per Kirchhoff's law, the total voltage rise is equal to total voltage drop. And when we cross 3 volt source, we are moving from high potential to low potential. So it's a voltage drop, and for a source voltage, irrespective of current in it, the rise and drop of voltage is equal to source EMF magnitude. So voltage across this source is 3 volt drop. Now we in our travel through loop cross this 2 ohm resistance, and in this 2 ohm resistance we are traveling against current direction. Current moves from high potential to low potential, and we are against current moving from low potential to high potential. So it's a voltage rise. Amount of current is I, so this voltage across 2 ohm resistance is 2I. So this 2I is a rise. Similarly, when we cross 3 ohm resistance from B to N, again we are moving against current direction. Current moves from high potential N to low potential B terminal, and we are moving from low potential to high potential. So it's a rise of 3I as per Ohm's law, I into R. And now finally when we cross this 2 volt source, we are moving from low potential to high potential, and it is again a rise of 2 volt, and summation of all voltage rise become equal to summation of voltage drop. Simplification of this KVL equation results in 5I equal to 3 minus 2, or circuit current, which we have assumed I, becomes as 1 by 5 or 0.2 ampere in this direction. Now the positive answer of current indicate that assumed direction and actual current direction are in the same direction. Now we can find out potential difference between A and B, and we will travel from B to A through M point, and in this travel in the direction of current, 2I will be drop from negative to positive, low to high. 3 volt is a rise, and amount of current is 0.2 ampere, and this drop considered as negative voltage and rise considered as positive voltage, and net result is positive 2.6 volt. That means from B to A voltage rise of 2.6 volt has taken place. So potential difference between A and B is 2.6 volt, and A is at high potential. Now the same calculation will result when we travel from B to A through N, and now both 3I and 2 volt is a rise, so taken as positive, and results is again 2.6 volt. Positive value means A is at high potential. This competitive exam problem will enhance our conceptual clarity. It is given that two voltage source 4 volt and E magnitude are connected to 3 resistance 1 ohm, 10 ohm, 2 ohm as shown in this diagram, and an ammeter measure current of 10 ohm as 0. We have to find out the value of this unknown EMF E. Now when this ammeter shows 0 reading, it means current in 10 ohm and this ammeter is 0, and with 0 ampere current in any resistance branch, the voltage drop is 0. So voltage across M and N is 0. That means if we travel from N to M, the voltage drop in 1 ohm become equal to voltage rise across this 4 volt source. So 1 ohm voltage 1x is equal to 4, gives me the value of this current x equal to 4 ampere. Now the same x current, as Mn branch has 0 current, passes through other branch of EMF and 2 ohm resistance, and when we move along current in 2 ohm resistance, there is a 2x drop, and when we move from low potential to high potential, there is E rise, and since M and N got a potential difference 0, that means the voltage drop of 2 ohm resistance is equal to voltage rise of E volt, and voltage of 2 ohm resistance with X current, and X is 4 ampere, is 8 volt. So EMF E got a value 8 volt. The solution of this problem will improve both subject understanding and confidence level. In this complex circuit, we have to find out potential difference between M and N nodes. And to find out potential difference, we have to travel from M point to N point and cross all circuit elements and determine their voltage rise and drop, and the net result of voltage rise drop calculation will be the desired potential difference between M and N point. Now to determine rise drop across all resistive element, we have to find out their currents, and for that purpose we have to first determine current Z in this BC section of 20 volt source and 20 ohm resistance, and it is not 1 ampere as this 20 volt is not entirely across 20 ohm. Let current in 2 ohm branch at this junction is X, and same X will travel and cross 3 ohm resistance and become incoming current to junction B. So at this junction, as per Kirchhoff current law, incoming current X become equal to outgoing current X plus Z, and simplification results as Z equal to 0. And that's also true. This 20 volt source and 20 ohm resistance connect two section of circuit by a single wire, and single wire doesn't make a completion of electric circuit or pathway for current flow in circuit. We need a completeness of circuit, and single wire connection is a open circuit condition, and current will not flow through such single wire connection. In fact, these EMF source are only the driving power for electrons. They won't produce electrons for current flow. They just only drag electrons if circuit is complete. Now these other two sources, 10 volt and 6 volt, are part of independent complete circuit, and it is quite easy to understood that current of 5 ohm, 3 ohm, 2 ohm is a single path or the same, and this 10 volt divide among 5 ohm, 3 ohm, 2 ohm. So this 5, 3, 2 are in series, and across this total series equivalent resistance 10 ohm, when 10 volt is applied, current is 1 ampere in this loop. So X amount is 1 ampere. Similarly, in this second independent loop, 1 ohm, 2 ohm, 3 ohm are in series, and across equivalent resistance 6 ohm, 6 volt will produce 1 ampere current as Y current as shown here in this diagram. Now to find out potential difference between M and N, we will travel from M to N through this circuit, and on our way we will find voltage rise and drop across all elements, and we'll take drop as negative and rise as positive. So our journey from M to A across 5 ohm is along the direction of current, and current moves from high to low, so it is high to low movement. That means a voltage drop. Current is 1 ampere, so across 5 ohm voltage of 5 volt will drop. Similarly, there is 3 volt drop, and now we travel across this 20 volt source from positive high potential terminal to negative low potential terminal. So this 20 volt is again a drop, and drop is taken as negative. Now there is no current in this 20 ohm resistance, so there is no rise or drop of voltage across 20 ohm. In place of 20 ohm, if we have placed another resistance, say 5 ohm or 60 ohm, our results will not change. Now from C to N, we are traveling across 1 ohm against current, and as current flow from high potential to low, and we are moving against current from low to high. So this 1 ohm resistance with 1 ampere current will have 1 volt rise, and again high potential to low potential there is a 6 volt drop with negative sign, and resultant is a 23 volt drop. So M and N got 23 volt potential difference, and M is at high potential. We hope this small video has explained each and every part of both KVL and KCL. Another video of same playlist can be used to understood application of Kirchhoff's law in real exam like conditions. Our other class 12th physics videos are very useful to enhance your subject understanding and scoring ability. You can also use them in your studies and share them with your friends. For our online classes and study notes, you can also join our YouTube channel membership by just press join button, and you can avail our question answer QA sessions and customized notes. Happy learning. Thank you very much.